study groundwater, but I love the surface of the earth and landforms. I was on sabbatical a few years back when I got an email, and being on sabbatical, you try to divest yourself from the university and not be involved in the daily workings. So I suppose I was a little less conversant than I typically am, rather minimally conversant. And then this person pestered me a bit more, and I finally said, well, this person's really determined. So I opened up a conversation, and it was Maraina who was contacting me because her husband, then boyfriend, fiance in the midst of all that, said that he recommended that if she wanted to become a glacial geologist, she could get the training she needed at Slippery Rock University. She had a bachelor's in fine arts and ceramics from IUP. So I said, you know, yeah, I love glacial geology and I can tell you how to work the academy and help you get to your goals, but you are an artist and you want to be a scientist, and there's going to be a lot of math and tough science classes between where you are and where you want to be. And she said, I don't care. I formulated a dream and I want to make this happen. And I said, well, then come on over and let's get busy. So she went on a research expedition with me that summer before she even took a class at SRU. And I can remember one particular night where there was a huge supercell thunderstorm. And I would very much not like to drive into that thunderstorm, but my field collaborator said the field site is right under that storm. So we drove into that storm and made camp that night. And it was a very tumultuous evening. And we were sitting in the car with the stove outside cooking. And Maraina said, I'll cook. And she stood out there in the rain and bopped in and out of the car. And I was later on able to say, when I was asked, would she be good company in Antarctica? And I said, I have seen her stand outside in the thunderstorm and cook a dinner and have a smile on her face. She's just so happy to be out in the field. She then did an independent study with me, and this is a literature review, and it's got a lot of impressive, tough science papers in it. It took her a year and a half to do. And when she handed it to me, she said, I didn't put any paper in here, Dr. B, until I read it and understood it. And it is about paleoclimatic proxies. We haven't had weather stations on planet Earth for the last 100,000 years. So we have to turn to nature with records of pollen and lakes drying up and things like that to figure out what the climate of the past was, coring through glacial ice. And I do recognize from speaking to her applications to schools that it was her work as an undergraduate at SRU that got her in the track that she's going to tell you about. And something that I believe to the core of my heart is that while Maraina was working here as an undergraduate at Slippery Rock University, she was doing a literature review and struggling to understand complex science and performing at the caliber of a doctoral candidate in a PhD program. So she was working as a doctoral candidate in quality while she was an undergraduate. And if you are a professor looking to have someone work on your PhD program, it's very comforting to have a candidate apply. And then as you learn their story, you realize that they were already doing doctoral caliber research. And so take it away, Maraina. Tell us what's been happening up there at the University of Maine.
Hi, great. Thanks for that introduction. I'm having some problems sharing my screen here. Usually I click share screen, go to advanced settings, and there's an option to share a portion of the screen. Does anyone know if there's something different here that I'm missing? Maybe.
I have it set for everyone to share screen. I made you a co-host.
Okay. Let me, sorry about this. Maybe Zoom updated and moved the tool that I used to.
Zoom did do an update, and actually I ran into trouble with that the other day because my share screen stuff was all funky, but I fixed it all. Do you want to try to email it to me and I can share it, or?
Actually, let me just hit it like this and see if
Started sharing screen. There it goes. Yep, you're good.
The point is so I can see my notes and you can't see my notes. Can you see my?
No, you're good.
Okay, the slide and you can't see my notes.
There you go.
I mean, I guess it's not that bad if you can see my notes, whatever, but all right. Okay, so we're all set up and good to go. Thanks for the introduction. Let's see if this works. Okay, still just the slide, no notes, right? Okay, good. All right. So hello, everyone, and thanks for tuning into my talk. Today, I'll be talking about my research at the University of Maine. I graduated from Slippery Rock in the summer of 2018 and began a master's program here at UMaine that fall. I'll technically be starting a PhD here in the spring. However, I'm working on both of those projects at the moment. Both projects are focused around dating glacial landforms to learn something about the Earth's past. For my master's thesis, I've been using glacial geology to see how much of the Antarctic ice sheet. Oh, sorry, it was the chat beeping, sorry. I've been using glacial geology to see how much of the Antarctic ice sheet will likely contribute to future sea level rise. For my PhD, I'm focusing on using the glacial geologic record in Maine to learn about the climate of the past 20,000 years since the last glacial maximum, which is this figure on the slide. So actually both of my projects focus on what's been going on with continental ice sheets since the last glacial maximum, or LGM as I'll probably call it from here on out. I'm going to take a different approach from the usual talk format and start with the methods before diving into how I've been using them. To start, glaciers flow. Both of these are time-lapse images from glaciers taken over the course of a summer, about 4 months. The glacier on the left is from Austria, and the one on the right is from Alaska. These are both time-lapse images over 4 months. So in general, glaciers don't move very fast. If you sat there all day, you likely wouldn't see anything happen. That's why time-lapse imagery is really important for visualizing how glaciers move. And as they move along, they pick up sediment. In this cartoon, ice is flowing from the left of the screen towards the right. As it moves along, it picks up pieces of the bedrock and carries it along with it. Rock falls from the steep valley sides can also fall down on top of the glacier and get taken downstream as well. The sediment, ranging in sizes from really fine-grained sediments like a powder to house-sized boulders, is dropped out of the glacier when it reaches the glacier's edge or terminus, and it forms a pile called a moraine, which is this part right here. Here's an example of a moraine from Koettlitz Glacier in Antarctica. This moraine is just a few thousand years old, and in the desert climate of Antarctica, it has preserved its shape pretty well. The ice that you see on the right is the ice that deposited this moraine. So a couple thousand years ago, it was over here. It was where I was standing to take this picture. And this debris melted out of it then. You can see the debris inside of the ice here, depending on the size of your screen, I guess. But these dark layers have a lot of debris, and there's a couple boulders in this. So once this glacier continues retreating, there will be another ridge forming right here once that's all melted out. So this boulder right in the very center is a prime example of a great sample. It's deposited on the crest of the moraine. It's made of granite. We'll get to that in a moment. And it doesn't appear to have rolled or shifted around in the recent past. I'll also probably be commenting on this as I go. Sorry. So let's pretend that this cartoon is that very boulder and that this glacier is Koettlitz Glacier. So the boulder melts out of the glacier and onto a moraine ridge. As it leaves the safety of the ice, it's exposed to incoming cosmic rays from outer space for the first time. These cosmic rays are from supernova explosions way in deep space, and they're constantly bombarding the Earth's surface. If it's been exposed before, it'll give a much older age than that of the moraine. We might see some of that later in the presentation. So again, these cosmic rays originate deep in space, and they're constantly bombarding the Earth at a relatively steady rate. As they bombard the boulder, it causes reactions within the rock. Our ideal sample is something with a lot of quartz in it, like granite. This is because when the silicon and oxygen in quartz are bombarded by the cosmic rays, the big pink bam in the side of the slide, a spallation reaction occurs. The cosmic rays have such a high energy that when they hit the oxygen in the quartz, it fragments the nucleus and beryllium-10 forms. Beryllium-10 only occurs on the Earth from cosmic ray spallation reactions. And this occurs mostly within rocks, but some does occur in the atmosphere. So when we do our final calculations, we take that little bit into account. So these spallation reactions affect a couple of different minerals within the rocks. So feldspar, calcite, olivine, but the quartz and beryllium-10 combo is most widely used for glacial geology. The olivine and helium one is really useful for volcanics. So back to the boulder. As it sits on the surface, left behind by the retreating ice, the cosmic ray bombardment continues, and the beryllium-10 builds up within the surface of the rock. The cosmic rays don't penetrate very far into the rock, so the beryllium-10 is concentrated within a thin layer on the surface, a couple inches thick. Thus, we sample just the surface of the boulder. So here I am collecting a sample along a moraine in Antarctica. This is a decent granite boulder within a glacial drift unit that extends up the side of a cinder cone. So you can see this is all very granite-rich glacial drift, and then this is all a cinder cone. So it's red and black. It's a very distinct drift limit. The cinder cone is the absolute worst terrain for hiking on, but when you're hiking on it, it kind of feels like you're on Mars. So that's pretty cool. And on the right is a sample from Katahdin from this past summer, I think July. So notice that we just sample the very top surface. The sample is only an inch or two thick. And that's because that's where the beryllium-10 is concentrated. So once the adventure is over, the samples come back to the lab where I weigh each sample and draw it. I just outline it and measure the thickness in multiple places to get an average thickness. This average thickness goes into the final calculations for determining how much beryllium is in the rock. Then I get to subject them to the loud crushing and pulverizing machines in the basement. This is the last thing those rock fragments see before being turned into a fine sand. So what comes out is this fine sand, and I sieve it to the correct size, the one that works best for our sampling method. And then that fraction of the rock is subjected to various intense acids, beginning with a brief boil in hydrochloric acid and finishing off with a sonic shake in a 2% hydrofluoric acid, which is very toxic. We use the concentrated hydrofluoric to add it to these. So these are the samples. The sand is in these jars, and we fill it about halfway with water and then some pumps of the concentrated hydrofluoric acid, which is very toxic and is why I sport this beautiful safety suit every time I go in to decant my samples. So after a month or so, everything but the quartz has been eaten away by the acid. And this leaves behind a clean white quartz sand, or tan. This one's kind of tan. This clean quartz is then dissolved, and then about a week's worth of chemistry strips everything else that might still be remaining and leaves the beryllium. So this is my favorite step of this process. There we go. Okay, the dissolved sample. So the quartz has been dissolved, and we're trying to get just the beryllium. So that dissolved sample is pipetted into a bed of resin. This yellow stuff is the resin. And if there's any titanium in that sample left over, just like a trace a little bit, it turns bright red. And then we add more acid, and it washes the titanium band down the sample column and into the waistband and out of our sample. After it's gone, we put the sample collection vial underneath, add more acid, and then just the beryllium-10 comes out. So it's cool. It's pretty to watch. This is a time lapse. This process takes at least half an hour or more. After everything is removed and only the beryllium remains, it's precipitated out of the solution. So it's turned back into a solid. And it forms a small, tiny white pellet the size of a pinhead. It's really small. And that is loaded into a cathode, which is a small metal tube that has a compartment at the end for the sample. Oops, trying to get to the next slide. There we go. Okay, and then we ship the cathodes out to California, to Berkeley, where they're run through one of these room-sized beasts. This is an accelerator mass spectrometer, and it's used to count the number of atoms in a sample. Once a sample is run, we then know exactly how much beryllium-10 was in the sample. And from there, we add in a bunch of factors, including the sample thickness and the cosmic ray flux and a bunch of things. And from there, we can calculate the date of when that boulder dropped out of the glacier. So you might be thinking, that's cool, but why does it matter when the glacier dropped off that rock? So to answer this question, let's dive into what I've been doing here at UMaine for the past 2 years. And a brief explanation of this photo. This is Walcott Glacier, which you'll be hearing a lot about in a minute. This glacier right here. And this is the Royal Society Range, the mountains right behind it. So we camped just off the side of the screen over here and hiked in to collect samples. So again, we'll start with the Antarctic research. During the last month, the first slide that I showed, grounded ice expanded out to the continental shelf margin. That's here in blue. So grounded ice means that the bottom of the ice was in contact with the floor of the ocean. And again, the LGM line is shown in blue, and the current grounding line is shown in orange, although most of this on this side is actually on land. My work focuses on what happened in the Ross Sea area, so this red circle in the center, during the LGM. And my field site is this red star right there. For a general reference, New Zealand is this way, and South America is up here. So the grounded ice expanded out into this Ross Sea, filled all of this blue area 20,000 years ago. There are two conflicting ideas as to what caused this to happen. The first is that the Antarctic ice sheet generally thickened and all of the glaciers expanded out into the Ross Sea to form the grounded ice. The second hypothesis is a bit more complicated. It states that the grounding in the Ross Sea was caused by marine mechanisms, such as a lowered sea level, causing previously floating parts of the ice sheet to ground. So think of an ice tongue that's floating, sea level decreases, it goes down and is in contact with the ground. In this case, let's see, where am I at? In this case, the interior ice thickness would have remained the same or maybe even thinned. We'll get to that later. These two hypotheses have very different outcomes if projected into the future. The first hypothesis implies that we can expect a lot of meltwater from Antarctica as a whole as the climate warms. The second hypothesis says that parts of the ice sheet that end in the ocean are likely to collapse, but the interior of the ice sheet stays relatively static over time. Discriminating which of these ideas is correct is necessary to figure out how much the sea level will rise in coming centuries. And just for reference, the West Antarctic ice sheet is this part. So it's kind of like the elephant's trunk. And then the East Antarctic ice sheet is this part, which is like the ear and the head of the elephant. That's how I think of it. But this West Antarctic ice sheet.
Excuse me, Maraina?
Yep.
If you're pointing to anything on your slide, I am not seeing anything that you're pointing to. So I don't know if you're pointing to the slide that's being shared. Like if you've got two screens, you might be pointing on one and it's not showing, but I don't see anything that you're pointing to. It could be on my end too, I don't know. I think someone else may have had the problem in the chat.
I'm having the same problem. So maybe instead of pointing, you can just say like upper left of the image or something like that.
I could do that.
I actually see a pointer, but it's under hypothesis over glaciers and it doesn't move.
Interesting.
Yeah, it's
Alright.
not moving either. So
Cursor.
Yeah, so
Uh,
anyway, I thought I'd point that out. Didn't mean to
Thank you.
interrupt because this is so
No.
fascinating, but I can't see what you're pointing to.
Yeah, no, this is strange. All right, so just disregard the arrow because it's not doing what I'm telling it to do, and I'll explain things. So there's a figure in the center of the screen, and if you use your imagination, if it's a cloud in the sky, it kind of looks like an elephant. Like there's a trunk on the left, and then on the right is like a big ear. It's like a larger mass. So the left, the little skinny thing, that's West Antarctica. And that holds about 3 meters of sea level rise. But most of those glaciers end in the ocean. And on the right, the larger mass holds about 58 meters of potential sea level rise, but it mostly ends on land. So that's a difference between the two of them. Let's see. So basically, the summary, there's two hypotheses and they conflict. Like what happened in the Ross Sea 20,000 years ago? The first one thinks that all the glaciers got really thick and they expanded out and the grounded ice happened because of that. In that case, all the little local alpine glaciers that are just fed by little ice fields would have thickened too, because everything was thickening. However, in the second hypothesis, those local alpine glaciers, if everything wasn't getting thicker, they expanded either. In fact, they may have thinned. And the grounding of ice in the Ross Sea was caused by a lowering of sea level, decreased melt along the margins, that sort of stuff. So move on to the next slide. So in order to test these ideas, I carried out fieldwork in the Royal Society Range along the Ross Sea. This is an image from Google Earth looking to the northeast towards Ross Island, up in the top right corner. Open ocean is just to the left of Ross Island and to the top of the screen. The South Pole is to the bottom of the screen, just to get you oriented. McMurdo Station is just to the left of the arrow for Ross Island. So we flew from that arrow, near where the box for Ross Island is, to the left side of the screen between Walcott and Houchin Glacier. And we camped there and hiked out to collect samples. We camped there for about a month. My field area consists of Walcott, Houchin, and Koettlitz glaciers, all of which are local alpine glaciers, which means they're fed by a local ice field and not connected to the Antarctic ice sheet. However, Walcott and Houchin end on land, so they're analogous to East Antarctic outlet glaciers, but Koettlitz ends in the sea. So during the LGM, ice filled the Ross Sea. Now I can hear the chat dinging and I feel like I should look to make sure that I'm not doing something wrong.
no, it's not. It's people
Okay.
coming in or out of the meeting. Yeah, you're fine.
Okay. All right. Wanted to make sure my mic wasn't going out or something. Okay. So the grounded Ross Sea ice filled the area where the Ross Sea square is up in the top center and backfilled down the screen towards where it says Koettlitz Glacier. It expanded landwards up to the red dashed line. Be useful to have a pointer, I'm sorry. But so it thickened and expanded up to that red dashed line. The red dashed line is thicker in the northern section, so right underneath that Ross Sea box at the top, and it's in a lower elevation down near Koettlitz Glacier. So that means that it was deposited by grounded Ross Sea ice and not an expanded Koettlitz Glacier. It also contains shell, and the rocks that are in it are from Ross Island. So the goal of my study, this area is important because of its potential for interactions between local alpine glaciers like Walcott and Houchin and the grounded Ross Sea ice. The goal of my study was to see whether these local glaciers expanded eastward to the red dashed line, so Walcott and Houchin, which would support hypothesis 1, or if they behaved out of phase and retreated while the Ross Sea ice expanded, which would support hypothesis 2. To carry out this project, I used the following methods. I created a glacial geomorphologic map of surficial deposits, which you'll see 2 slides from now. I also collected samples of subfossil algae for radiocarbon dating. These algae grew in shallow, ice-marginal ponds and streams along the headlands moraine, which was that red dashed line in the last image. And they were formed as the moraine was being built. Therefore, the algae date the formation of the moraine. This cartoon shows the grounded Ross sea ice that would have been on the right-hand side of the screen in the last slide, coming up against the land. And as the ice melts, it comes down the side of the glacier. Oh, I'm pointing again, sorry. As the ice melts, it goes, meltwater goes down the side of the glacier and results in shallow meltwater streams and pools running alongside the ice. Algae loved growing in this environment, and it formed these nice big mats. However, there's a glacier right there, and glaciers are full of sediment. So as the meltwater picked up sediment, it would drop it off and bury these algae mats. And this process kept happening for thousands of years. So the headlands moraine is a stratified moraine with fine silt, sands, gravel, the few occasional boulder, with layers of algae inside of it. And once the Ross ice sheet retreated, the lakes, the ponds dried out, the streams dried out, and the algae was essentially freeze-dried. So the algae samples, after we collected them, were sent to Woods Hole Oceanographic Institution in Massachusetts for dating. I also collected samples from boulders for cosmodating that we went over in detail a couple minutes ago. Here's a nice perched boulder. So the bottom image, this is in front of Houchin Glacier. That rock was put on top of that other rock by a glacier. So that's a perfect sample. Next slide. I wanted to include this image. This goes with the radiocarbon information. This is the headlands moraine. This image is taken from standing on top of the headlands moraine. The grounded Ross sea ice would have filled the area on the left-hand side of the screen. And this is the moraine on the right-hand side of the screen that it formed. Tess is laying, she's another graduate student who just graduated. She's laying on the ice contact slope. So that's the slope where the ice was. And she's digging for algae. We spent a lot of time laying on the ground digging for algae, but we got a lot of samples. For reference, Walcott Glacier, I guess I can't point, is in the very back center. There's that little patch of ice. You'll see that again in a moment. So this is the glacial geomorphologic map. I mentioned 2 slides. If I could point, I could show you where the image was taken from, but in general, it was taken from the top right of the screen, looking towards the bottom left of the screen in the last slide. So Walcott and Houchin glaciers are on the left, Ketlich is on the right. And Ketlich has expanded out into the area that was once filled by that grounded Ross sea ice. Grounded Ross sea ice expanded westward multiple times. So from the right-hand side of the screen towards the left-hand side. And as it did that, it deposited these units that I've drawn in shades of orange. So the darkest orange, which is the biggest unit there, is the LGM deposit. So it's about 20,000 years ago, give or take. We'll get to dates in a moment. There's older instances of the Ross Sea expanding, and those are in lighter shades of yellow outboard of that. So there's one around 56 and then another one around 150,000 years ago. Alpine deposits are drawn in shades of purple, with the darkest purple being the most recent. This includes an alpine deposit along Ketlich Glacier, because Ketlich Glacier has expanded. We'll get more to that in a moment. One of the important things this map highlights is that there are cross-cutting relationships in the area south of Walcott Glacier. The Ross Sea drift, so to describe that, if you go to the 3-kilometer mark in the scale and go straight up, there's where the orange is overlaid on top of the purple. That's what I'm talking about. So this indicates that they advanced out of phase with each other, because the alpine glaciers came out, deposited one unit, and then the Ross Sea drift came in and deposited a unit over top of that, and they did not join each other. This is a simplified static image of those cross-cutting relationships. This image was taken from a helicopter looking south from above Walcott Glacier. The red and orange dotted lines are the Ross Sea drift from the grounded Ross Sea ice, and they're draped over top of the purple Walcott 3 moraine. So once I had an understanding of the deposits, I wanted to develop a chronology for the drift units. So I'm going to show two areas here where I have more detailed information in terms of radiocarbon ages. On the left will be that box in front of Walcott Glacier, zoomed in, and on the right will be that box in front of Houchin. So I'd like to draw your attention to the dates along the border. So all of these dates were collected along the Headlands moraine. There was the last image with Tess laying on the moraine. So they're all from that area. And these ages indicate that the grounded Ross Sea ice reached its maximum in the area around 18,000 years ago and stayed there until about 14,000 years ago. An interesting point is this one date down by Koettlitz Glacier. So that's on the right-hand side of the screen, at the very bottom in the purple, there's a 6.5 plus or minus 0.07 Ka. So it's 6,500 years ago. This algae is different from the Headlands moraine. This algae formed in the bottom of a lake where there was no ice, and then that lake, those sediments from the lake were thrust upwards by an advancing Koettlitz Glacier. The Koettlitz Glacier came and kind of like bulldozed those lake sediments up, and now we can sample them. So this means that Koettlitz has advanced within the past 6,500 years during the Holocene. I also collected samples for beryllium-10 dating. Most of the results that I have so far are in the area around Walcott Glacier. So we'll zoom in there. Again, radiocarbon ages are in green. They're on the right in the orange. And the beryllium-10 ages are in white and blue, mostly on the left. Again, the grounded Ross Sea ice expanded from the right side of the screen towards the left-hand side, depositing those orange units. And they reached their maximum during the LGM around 18,000 years ago. However, Walcott Glacier, if we jump to the left-hand side of the screen, hasn't expanded significantly since 35,000 years ago. So between 35 and 45,000 years ago, that expanded outwards. But since then, it has not. It did not expand out to contribute to the grounded Ross ice during the LGM. So some preliminary conclusions from this research are that the grounded Ross Sea ice expanded landward several times, with the most recent reaching its maximum around 18,000 years ago. The alpine glaciers have expanded in the past. However, the most recent expansion was between 35 and 45,000 years ago. Thus, the alpine glaciers did not expand during the LGM, and actually, they appear to be expanding at present. They're overriding their last moraines. So what does this mean? Well, this supports hypothesis 2, at least in the McMurdo Sound region. Land terminating versus marine terminating glaciers behave out of phase. How could this happen? Don't glaciers expand when it gets cold and retreat when it gets hot? Well, not always. Warmer air holds more moisture than cold air does. So in Antarctica, when the temperature's warm, it snows more. Since there is little melt on the surface of the glaciers due to the year-round cold temperatures, glacier size is pretty dependent on the amount of snow that they get. So basically, warmer temperatures equal thicker ice to a degree, at least for glaciers in the sea. Here's a figure showing a doubling of accumulation rate after the LGM. Again, it'd be nice to have a pointer. But on the bottom are thousands of years, tens of thousands of years ago, 70,000 years ago on the left, and today at 0 on the right. So if you go to 20, that's the LGM. You pop up to the red squiggly line. You can see that accumulation is pretty low during that time. But right after that, if you move to the right, it jumps up suddenly. And that is the termination. That's the end of the last ice age. Things started warming up. And at that time, there's a lot of precipitation over Antarctica. But glaciers that do end in the sea are subject to the warming ocean temperatures and increased melt along their bottoms. So they behave more like the traditional glacier model. During cold times, they get larger. During warm times, they get smaller. And that's how we end up with glaciers that end on land, expanding during periods of warmth, and glaciers that end in the ocean, retreating. But somewhere there exists a threshold where the warmer temperatures and the increased accumulation no longer matter. Finding that threshold is the subject of future research. What this means for the coming centuries is that land-based portions of the ice sheet might actually increase just a little bit in size. However, the marine-based portions of the ice sheet are likely to continue collapsing, like West Antarctica. So in general, the 58 meters of potential sea level rise will likely stay locked up in East Antarctica for at least a while. But the 3 meters that are locked up in West Antarctica is slightly concerning. And there's lots of research being done on that right now, especially the Thwaites Research Initiative. If you Google that, you'll find quite a bit of information. And that concludes what I've been working on here in Antarctica. And let's hop over to Maine real quick. This is research that I'm just starting for my PhD, so it's in nowhere near as detailed as what I just went over. I just started this summer. So these pictures are from up on Mount Katahdin, which is in north central Maine. It's the largest mountain in Maine and the end of the Appalachian Trail. On the left is a nice perch boulder that we sampled in July. And on the right is a view from Hamlin Ridge looking towards Baxter Peak. So Baxter Peak is in the center of the skyline and the back of that. So I have one LiDAR image here. So one thing that spawned this research is the release of really detailed LiDAR for the area. Got lots of people excited. So this is the summit of Katahdin, where the blue star is. And just in case your eyes are inverting things, which mine do all the time, the blue star and everything to the left is a high elevation. And then the contrasting stuff to the right of that little bowl-shaped thing is a steep cliff face going down. So my eyes like to flip this all the time. And then on the right, there's a bunch of blue arrows pointing to a lump going along the base of the mountain. That's the Basin Ponds Moraine, and that's where I will be Friday and Saturday collecting samples. So I wanted to zoom in on Google Maps here for a second. So I'm gonna just exit this presentation, I guess, for a second. Maybe I can minimize it. No. There. Do you see anything on my screen? Oh no, it's paused. All right. Let's try this new share. Let's try that. Sorry, there's always technical problems. All right, this might not work. Google Earth Pro is not responding. I guess it doesn't like trying to present during a meeting. All right, well, we'll just skip over that. Let's go back to the PowerPoint. Oh, wait a second. Come on, Google Earth, you can do it. No, I guess Google Earth can't do it. Oh well. Goodbye, Google Earth. All right, so I'm going to share my presentation again. Oh boy. All right, let's scroll down through here. Just a second. Sorry about that. Now my computer is making noises. It's not happy that I tried to do that. All right, so we've been up to Katahdin twice this summer. The first time we started on the ridge in the top center. We hiked up through there and collected samples along the ridge from its base to the top. So we're hoping to use these samples as a dipstick to see how quickly the ice thinned at the end of the last ice age. So we collected samples along that ridge, and there's a couple other ridges where we'll be collecting samples, and also along the tablelands, which is the left side of the screen, that lighter color. We'll also be collecting samples, I think I mentioned it, along the basin ponds moraine, which is where those blue arrows are, and all the little moraines that are outboard of that too. There's quite a bit of glacier in Baxter, and there's been some work on dating them, but that work was done right as the Cosmo dating was just starting to come into style. So there's been a lot of advances in that method since that research was conducted. So we hope to get something that's a bit more detailed. Yeah. We're also going to be coring lakes. There's a proposal being put together right now that includes all of this glacial geology in Baxter and some lake cores from just south of Baxter. So that pretty much concludes what I have for the Baxter stuff at the moment. You can ask questions at the end, but I do have a couple pieces of advice that I wanted to just tack in at the end here. So come on, you can do it. There we go. All right. Being a student in the age of COVID advice. This is crazy. All the time, it's just crazy.
We're still looking at, oh, there it is. Okay.
Oh, okay. Sorry. I think my computer's being a little slow. I think it's having a temper tantrum because I tried to load Google Earth. Sorry. So my first suggestion is to designate a working area. That's something I struggled with at the beginning of this, but I've set up my little desk space in a corner. And that is a place where I go and I sit down, and I'm now programmed to start working when I sit down in this space. It doesn't have to be a desk. The left-hand side of the couch is also my working space. It's great for sitting and reading papers. But having that, it's like your office, but it's not an office. So it just helps me out a lot. The second point is to keep a running log of your time during the day. This is something I just started doing, I guess, right when all of this started. And it's been really helpful. I guess you can, I don't know, I can't see myself, but that's how I keep track of everything. It looks like chicken scratch, and it is. But like, say I start working on my programming homework at 2 o'clock in the afternoon. In the 2 o'clock block, I write down 2 o'clock programming. And then when I'm done, I block out the amount of time that I spent doing that. So at the end of the day, I can look back and see how much time I spent doing things. It's kind of like a self-motivational thing. Like, I can look back and be like, oh yeah, I did stuff, because I'm prone to falling into the pits of despair. And this helps keep me out of that. I recommend it. You can use a regular planner. Keeping track of what you've been working on is really helpful. Last point is software advice. Many of you are probably familiar with this. It's called Mendeley. It's designed to keep track of academic papers, but it can be used for other things. I've been using it to keep textbooks. So if you keep your PDF in Mendeley, you can highlight it and add notes, and then read down through it. You get to page, 45. You hit the sync button at the top and it syncs it to your online, it syncs into your portfolio. So you can then go downstairs, hop on your laptop or a different computer, open Mendeley, hit sync again, make sure it's all updated, and bam, you're at that part of the book again with all your notes and everything. I've just found it really useful. So that's general in the age of COVID advice. And then one more slide. It's just general advice and general. And this has taken me a while to get. The first is the most important point, that your worth is not defined by your productivity. I struggled with this and I'm still struggling with it, but I'm getting better. So yeah, you're worthy, you're here. Just because you submit a bad paper doesn't mean you're a bad person. It's okay. And linked to that is perfectionism is the mother of procrastination. I have constantly put off things because I want it to be just perfect. And then in your brain, this thing that really isn't that complicated just starts growing because you want it to be perfect. And it goes from being this tiny little thing to this giant mountain, looming behind you. So don't try to make things perfect off the bat. Just start doing it in little pieces, little half-hour sections. The next bullet point, burnout, it's real and it's avoidable. I haven't completely learned how to avoid it, but I'm getting better. It's all a process. Linking back to that perfectionism and procrastination, like learning to conquer that really helps stave off burnout. And taking breaks, go outside, go for a hike. At least that's what I like to do. Next is just ask. Don't be afraid to ask questions. There are no stupid questions. Just ask. The answer might be something you had no idea about. After that is get in the van. You're all familiar with that. You know what that means. And then the very last point is remember that academics isn't the only component of your education. So yes, you're learning about science, you're becoming better scientists, but there's a whole world out there. So immerse yourself in it. Learn about things beyond what you're learning about in school, because that will make you a better scientist in the end. So with that, I would like to say, I would like my slides to change. Thank you. And special thanks to all of you that have helped prepare me for graduate school. With that, I'll stop the screen share and I'll take any questions.
All right, Maraina, that was awesome. Maraina really became a go-to person. So I agree with everybody that's clapping. Maraina became a go-to. All the faculty in different classes were asking her to accompany all of the field trips because she's really reliable. You're a credit to us all, Maraina. We have a couple minutes left before some students might have to leave for classes. So let me ask, first of all, are there any questions from undergraduates for Maraina? You can either type in the text box, the chat box, or just unmute and speak.
So I had a question for you about the Antarctic research. So you said, I mean, you're getting a big difference in the movement of the glaciers between the ones on the grounded ones and the more water-based. And there's a lot of age difference between them. Are you seeing changes or big differences in the rate of flow of the glaciers coming from like the Walcott and the Hudson compared to the Kodelitz Glacier? And could those be affecting the rate of deposition of sediment? So could you be getting slower deposition of sediment, I guess, coming off of the grounded alpine glaciers?
Yeah, certainly. So the alpine glaciers that end on land are frozen to the ground. So they move really slowly and they don't pick up a lot of sediment. Thus, their moraines, I guess I didn't really show any moraines close to Walcott and Houchin, but their moraines are only a couple meters high. They're not very big. So they move a lot slower and they transport a lot less sediment. Whereas Koettlitz Glacier, at least now, maybe not in the past, is wet-based. That's more like temperate because it goes into the ocean. So it moves a lot faster right now, at least. So yeah, there's definitely a difference in the amount of sediment being transported and how quickly it's being transported. Also, the glaciers that end in the sea tend to move faster in general. And they go out, and once they start to break off, it creates an uncorking kind of mechanism. So it goes back upstream and stuff further back upstream starts moving faster too. So that's what we're afraid is happening in West Antarctica. But yeah, does that answer your question?
Yeah, I guess I did a bit of a poor job of wording that, but I guess what I was kind of getting at is, could the slower rate of flow be having an effect on the ages of the sediment that you're seeing coming from each of those glaciers? Because if it's transporting less sediment over a longer time, it's picking up less and dropping off less, so it's not being exposed for as long.
I see what you mean. So the sediment, we're looking at the landforms that the sediment makes because they kind of are like the footprints. So the moraines along all the different types of glaciers are like the footprints of when that glacier came out to that extent. And even, it doesn't matter if it's a giant, like a giant moraine, or if it's just a little thing with like just a little bit of sediment, it still means that the glacier came out at that time and stayed put for a while. So we use it like a, oh, sorry, my computer is doing weird things. We use it, yeah, I guess as like dating the footprints of where the glacier was. So to answer your question, no, the amount of sediment doesn't directly influence the age and the amount of exposure that the sediments get. It's just that the moraines are smaller when it's moving slower and has less sediment. Does that make sense?
Yeah, that makes sense.
Okay. Any more questions?
Other questions from the students?
Sorry, the dogs aren't barking now. I put it in chat, but the dogs were barking at the time, so I didn't want to like ask it while they were barking. But my question was like, with recent changes in our climate, will this change like how your like studies like yours are executed, and will like current climate change affect the production of beryllium? Do you know?
That last one, I don't know. That's a good point, because the cosmic rays are coming down through the atmosphere and they do interact with everything in the atmosphere. So I'm not sure, I don't know. I doubt that it would really impact the amount that's being formed in the rocks, but as I said, a little bit forms in the atmosphere too, so it could affect that amount, but I'm not sure. If you look at the cosmic ray flux going back in time, it doesn't seem to go hand in hand with the amount of CO2 in the atmosphere. It goes by when supernovas are going off or whatever, the solar winds, a whole bunch of things go into that. Yeah. So in general, no, I don't think climate change will affect the amount of beryllium that's being formed in the rocks. And in regards to climate change, yeah. Just one small thing in Antarctic field work. So we go and we camp for a month out in the middle of nowhere. A helicopter drops us off and our food. Luckily, Antarctica is just a freezer. So you can have a cooler and fill it with stuff and it stays frozen. And with warming temperatures, our food gets soggy and melts. And yeah, that's not something that used to happen like 10 years ago. It was cold enough that they didn't run into that problem. So it's small things like that that are that I can think of off the top of my head that are affecting field work. When it comes to glacial terrains too, like as it gets warmer, things melt, landscapes become unstable, safety issues. So yeah, it definitely affects field work.
In the chat box, Tyler Miller asked you to comment on the importance of a field notebook.
I see that on a scale of 1 to 10. 25. So I have right here, I have both of my field notebooks for my current research, and I use them frequently. I also have scanned copies of these in my computer in case the house burns down, and they're copied to my Google Drive, and they are extremely important. And being detailed is also extremely important. Like I put in things just to remind me of the day, like what I ate, which direction we went, what I saw, because when you're going back through your notes, it's really helpful to be able to put yourself back in that place. So like I'll have for a day, like the entry, like which direction we hiked to get samples, interesting things we saw, if any. And then after that, I start with like the sample data stuff. So I have that reference point, and then I can look down and be like, oh yeah, I remember that sample. Yeah, and then all of this, like all the coordinates and a bunch of other data that we collect then gets copied into Excel. So we have multiple copies of everything. And yeah, keep a great field notebook and don't be afraid to write and write and write. It doesn't, just write as much as you can about where you're at. Yeah. Hi, Felix.
See the question about
Any more
wildlife
questions?
in Antarctica?
Oh, yeah. So we were kind of inland for penguins. Like penguins don't go to where our field site is. At McMurdo, they occasionally come over and hang out. There was one there one day, but it was one of those katabatic wind days where you don't go outside. So I did not get to see a penguin while I was there, which was very disappointing. But I did get to see a lot of seals. There's Weddell seals that you just want to walk up and hug them, but you can't because they'll bite your fingers off. But they're so cute. We saw a bunch of those. They do come landward. Apparently some males get confused and they'll go landward, I guess maybe to die. So they're mummified, couple 100-year-old bodies of seals in our field area, which is a little alarming to come across. So there's seals, and then there was skuas, which are big, nasty, mean seagulls that I was one day laying on the side of a moraine like Tess was, and I heard this like cackling noise, and I thought that Tess was standing up there laughing at me. So I looked up, and it was not Tess. It was those skuas on my backpack trying to take it. They thought they were going to make off with my backpack. So that's it. That's all the wildlife I saw. Seals and skuas.
So you were asked about sleeping and eating in Antarctica, and I'll add to that, how long were you in Antarctica?
Yes, so let me see if I can share a screen again. Share. All right, can you see that?
Yes.
Hopefully. Okay, yeah, so this is where we slept and we ate. We had 3 campsites, but they all are pretty much the same setup. The 2 yellow tents are the sleep tents, 2 people per tent. There are, I don't know, 7 or 8 feet. No, they have to be more than that. Between 8 and 10 feet square. So enough room for a sleeping pad and your backpack and stuff in there. And then the weird looking caterpillar tent on the right is our cook tent. So that's where we kept the stove and all the food. And there were 4 sample boxes that we used as chairs. And that's also where we hung out on days where the katabatic winds were so strong that we couldn't do field work. So by strong, I mean like 100 miles an hour. So you just sit in the tent and read all day. Yeah, so that's where we slept, where we ate. Bathroom, everyone always asks about bathroom. That is a bucket off to the left-hand side of the screen and down the slope, so you had a little bit of privacy, but it's the best view in the world.
Maraina, can you comment on McMurdo? I've heard some interesting stories about the crews that live there for months at a time and have various jobs. Did you get to spend much time at the station?
Yeah, so we had 2 weeks in the front of thing. Well, I guess a week and a half at the front of things where you go to McMurdo and you get everything prepared. And then we were in the field for a month solid. And then we came back and we got stranded in McMurdo for 2 weeks because there was a storm and the plane was broken and we got stuck there. So yes, I got to spend a lot of time with the people that live and work there. There are 3 bars in McMurdo, which is to be expected. I think I was watching a documentary. It's a Werner Herzog, and it's about people who live in McMurdo and scientists that conduct research. And one of them said that McMurdo is the place where all the strange people are shaken out of the world and they all fall down to the bottom. So everyone is a character and has a great story. I sat at the bar and talked to this guy who like owns racehorses and just decided that he wanted to work in the IT department at McMurdo for a year, like just for fun. So yeah, there's a lot of interesting characters and a lot of great stories.
So I want to ask one last question, and that is, you know, in textbook descriptions of sedimentology and geomorphology and so many different aspects, academics create models in idealized circumstances to develop a baseline of understanding. And in glacial geology, I'm teaching the students that moraines are composed of till that is deposited in a fashion to leave it massive. But you mentioned that the Headlands moraine is a stratified moraine. This is a violation of the model that I teach, And there's a very important lesson for students there, which is that we learn idealized models and nature comes at us in an unidealized manner. And that prompts us to do more science to understand why. So you were talking about algae in there, and I'm curious, is there a seasonality, summer and winter, in deposition of the moraine, or is there a seasonality, summer versus winter, in the growth of algae? Or can you just describe to us a little bit about how that particular moraine ends up with stratification in it?
Yeah, so that happens only during the summer and only for maybe a month, maybe 2 months. That is the only time in Antarctica where it gets warm enough that water can melt. So at that time, the streams form and the algae starts growing and goes to town, and then it would get covered up either by more sediment, or if the ponds were still active, they would freeze over and protect the algae underneath. So then the next year when that ice melts, the algae can continue growing before it gets covered by sediments. But there are lots of kettle lakes in Antarctica that freeze over on the surface, and the algae survives on the bottom throughout the winter. So yeah, the algae is
it's not a pure ice delivery mechanism, but there's seasonal melting, which also allows biotic growth. So the moraine is in truth being affected by a host of processes and not simply by deposition by ice. Comments?
right. Yeah.
Okay. Very
Yeah.
cool.
So the summer. Yeah. Yeah. You summarized it. That's okay.
Well, Luke asked about how much sediment, and then after that, I think we'll let you off of the hook, since it's not a dissertation defense. You don't have to stay here all afternoon.
Huh. I wouldn't mind staying here all afternoon. How much sediment? So those headlands moraines are about 5 meters tall if you're on the hill slope above them. So you're walking down the hill slope like this, and then there's a lump. It's about 5 meters tall. And then that slope goes 200 meters down to Koettlitz Glacier. So, but the moraine itself is about 5 meters. And keep in mind, it's been sitting there for probably around 14,000 years. So it has eroded a little bit. But on the scale of like comparing that with a glacier in a temperate zone, these are pretty little moraines and just a little bit of sediment.
Thank you.
Yeah.
All right, so let's give Maraina one more round of applause. And tell her again how proud we are of her and how grateful we are that she's willing to come back and put the extra effort in to share, giving back to the community. We really appreciate that. Any last comments from anyone? Otherwise, I'm going to end the meeting.
Well, thanks for having me. I'm happy to come back and talk. Sorry it's not in person.
Thanks, buddy. That was awesome. We'll be in touch.
Yeah, it was good to see you again. Thanks for coming out and talking to us.
Great. Well,
Yes, that was
bye.
very fascinating. Thank you very much.
Yeah.
All right, I'm going to go ahead and pull the plug on the meeting. Have a great day, Maraina.
All right.
And
Sounds good.
safe in the field.
See ya.